We're now up to part 2 of this networks unit, and today we're going to talk about planar graphs and Euler's formula. So, a couple of different types of graphs. So when a graph can be redrawn so that no edges cross each other, then the graph is called planar. Now, there's two examples here of how to turn into a graph and make it planar. So, this one up here on the left, all right, obviously it's got heaps of lines that are all crossing. What we can actually do is the two lines that are in yellow, now we could actually move that so that goes around there and this one goes around here, just like we've done here, and suddenly none of the lines cross each other. This one's slightly harder to work out, and some of them you find might be when we're trying to work out if they are planar or not. But if we were to move this vertex down to here, this vertex over here, and this vertex over here, you can maybe pause this and have a bit of a think around it and maybe even draw it yourself. You'll understand that it will end up spinning out like this. Again, we'll be able to realize that that graph is in fact planar. Other types of graphs, and we say that two graphs are isomorphic if, although they might be drawn differently, have the same number of vertices and edges, the same connections between the vertices. Okay, so I've got a couple of examples here, and it should hopefully be really easy for you to understand eventually. If we were to move D down to here, now obviously this edge would move and this edge would move and it would end up going down like this. If you have a look over here, that's exactly what we've done. Let's take that one step further. Let's move A and C. If we were to move this edge up over there, it's still the same connection, but it would end up looking like this. All of these graphs are isomorphic to each other. Euler's formula. Some people, in fact, it's probably meant to be called Euler's formula. I'm going to call it Euler's formula because it's what I'm used to. And this is the formula here. V plus F minus E equals 2. Now, you might not really understand what that's going to involve, but obviously V, maybe vertex, E, maybe edge. And that is exactly right. Here's a network we are going to work with. V, number of vertices in each network. F is the number of faces. Now, faces is a different concept that we need to get our head around. So let's take this example in. Now, we call each face the closed area in a network. So this is closed by those four boundaries. That's face 1, face 2, face 3, face 4, face 5, and the whole thing on the outside we actually call a face in itself. So there are 6 faces to this part. If you go down to this second example, well, there's 1, 2, 3, and the whole thing is the 4th face. So there's getting your head around that. Next up is the number of edges. We've gone through that, and you should have your head around that by now. So for this example here, we'll go V plus F minus E equals to prove that that is correct. So where V are the vertices 1, 2, 3, 4, plus the faces would be 1, 2, 3, 4, plus the outside is 5, minus the edges. So there's 1, 2, 3, 4, 5, 6, 7. 4 plus 5 equals 9, minus 7 equals 2. This is correct. So Euler's formula is correct for this.